Alright, so what we had seen was we have been able to understand how to solve a system of linear equation, how does the matrix multiplication helps in doing things. But what is more important is that there are a lot of equivalent conditions which were playing some role or the other when we had square matrices. Fine. So we would like to go further on those ideas and then understand things. That is one idea. The other thing is that solving a system of equation also led us to the study of vectors in some sense, in the sense that if I have a solution, then there was some combination of vectors which gave me the right hand side. If I am writing at Ax equal to b, then b was sum of certain vectors. Fine. So we would like to again go on those directions. So let us understand what are vectors. So the main idea for us will be now to understand what are vectors. All right. So let us write what the vectors are. So what we understand in R2 or R3, that you have a vector x, you have another vector y, then you can add them. X plus y is also a vector, Fine. Alpha times x is also a vector. So we had assumed that x and y are vectors, and therefore all these two happens. Not only that, we have that x plus y was equal to y plus x. We had x plus 0 vector is same as the vector x. For every x, we had minus x, such that this gave us 0. Then there was a notion of what is called associativity hold, that x plus y plus z was x plus y plus z. Fine. We also had the notion that 1 times x was 1. Fine. And there is this notion of distributivity that holds, that this is same as alpha times x plus beta times x. So we would like to take them as our definition of what are the set of vectors. Is that okay? So again, the last part will be something like x plus y times alpha is equal to alpha x plus alpha y. So when I am writing alpha here, alpha is an element of R, or in general it will be an element of F. Fine. Because sometimes we may have complex numbers for us. Fine. So the important thing to understand here is that whatever was true in R2 or R3, all right, there we had vectors, and those vectors had certain properties. We want those properties to be satisfied for any set of vectors. So we want the above properties to hold for any collection of vectors. Fine. So for us, definition is that let V be a non-empty set and F a set of scalars. So remember, scalars could be real numbers, complex numbers, fine. It could be rational numbers. It could be ZP. If you remember ZP, we had computed Z5. It could be ZP, P a prime number, fine, and a generalization of those ideas. But mostly we will be looking at real numbers and complex numbers, fine. But it could be anything. All right. So let F be a non-empty set and F a set of scalars. Then V is said to be a vector space over F. So F does play a role, that is important, over F. V is said to be a vector space over F if the above conditions hold. Above conditions holds means I have an addition between two vectors. So given this set V, given this set V, I have a definition of addition between two elements, I have a definition of a scalar multiplication there, and with that all these conditions are valid. That is more important for us. Is that okay? So, we already know that R2 and R3 are vector spaces. Let us look at more examples. And there are hundreds of examples, but we will not look at all of them, or just a few of them. All right. For example 1, let us look at R itself, the set of real numbers. Then I can add two elements of R. So, given any x belonging to R, y belonging to R, I can talk of x plus y. I have x plus y. I also have x plus 0 is equal to x plus y is same as y plus x, fine. We also have x plus minus x as 0, and so on. So, all the above properties are satisfied. Here it turns out that I can take f to be R itself, because a real number can be multiplied with real number to get a real number. I can also take f to be Q, set of rationals, fine, because rational times a real number is a real number. So, the multiplication by alpha, where alpha is a rational number, is a meaningful object, and hence I can say that the set of real numbers is a vector space over real numbers, as well as it is a vector space over rational numbers. It turns out that these two are very, very different objects, fine. Over rational numbers we will not be bothered about, because it is out of syllabus for us, but this is very, very important idea when you go for higher mathematics or higher places, all right. So, we will not be bothered about it, but this is very, very important. It leads us to the study of rationalization and so on, and lot of complicated things. 2. Example 2. You have already seen R2, R3 for you. We can also talk of Rn. N is any positive number for us. So, I can take it as this Rn is a set of collection of elements of the type x1, x2, xn, such that each xi belongs to R, 1 less than equal to I less than equal to n, fine, Rn. So, I can write this vector as x. So, generally I am not putting transpose here, but mostly we will be looking at, as I said, vectors are always column vectors for us. So, it will look like this x1, x2, xn. I will just write x in general. Similarly, I will have y, which will be y1, y2, yn. I can define x plus y as x1 plus y1, x2 plus y2, xn plus yn, and alpha times x as, I can define it as alpha x1, alpha x2, alpha xn, all right. What is important is that this is the right way of doing things, but addition and multiplication is in our hand. It is in our hand. We can choose these definitions in such a way that that set that we are trying to study is a vector space, all right. It depends on us how to define these objects. Nobody is going to dictate. It is you who has to decide which to take, which not to take, and why, fine, depending on different issues. I will take some more examples. Example 3, let us look at Rn. We have already looked at complex number Cn. So, now here I will have vectors are going to be again x1, x2, xn. Each xi belongs to complex number 1 less than equal to I less than equal to n, and again I can have the same thing, x plus y is x1 plus y1, so on till xn plus yn, and you have alpha x as alpha x1 till alpha xn, fine. Important, alpha can be real number, alpha can be complex number. Fine. So, what we are saying is that Cn is a vector space over R, Cn is also a vector space over complex number, Cn is also a vector space over rational number. And all of them, they have different meanings, they have got different ideas. So, you have to be careful about them, what you want to study, and be careful about it. For example, here in this case, all right, I times, so I times the vector 1, 2, 0, 0, 0 is not equal to I, 2I, 0, 0, 0. Does not make sense. This is important, all right. Does not make sense. Why it does not make sense? Basically because I is not a real number. Right. As vectors, as vector, this is a vector, this is a vector, these two are vectors, they are fine, but this scalar multiplication is not allowed. A scalar multiplication with complex number is not allowed. Fine. So, this is important when you are talking of complex number Cn as a vector space over R, you are not allowed to multiply by a complex number, you are allowed to multiply only with real numbers. Similarly, here you are allowed to multiply only with rationals, here you are allowed to multiply with everything. Allowed to multiply by complex numbers. But there it is not allowed. That is what you have to be careful about. Fine. So, whenever you are looking at things, be careful, that is all it says, nothing more than that. Some more examples. Fourth, we had looked at the solution system. So, suppose I have got a matrix A is m cross n. We had looked at the system all x belonging to Rn such that Ax is 0, all right. This was called the solution set of the homogeneous system. Homogeneous system, fine. So, look at here. So, if what we have already seen that if x1 is a solution, so let me write this as V. So, if x1 and x2 or x and y, let me write x and y. So, if x and y belong to V, this implies that x plus y times A is Ax plus Ay, fine. Xy belongs to V implies Ax is 0 and Ay is 0, and therefore, this will together imply that this is 0 plus 0, which is 0. Not only that, A times alpha x is alpha times Ax, because alpha is a scalar, say R, I am looking at over R, so R here. So, this is same as alpha times 0, which is 0. So, therefore, if you see, we are able to define vector addition and multiplication, and you can check that all the conditions for V being a vector space is satisfied. So, therefore, V is a vector space. Vector space over R. Why over R? Because we looked at the system over R, all right. So, this R is related with R here, all right, or this is also related with assuming that this has real entries. If you had looked at complex numbers, it could have been over complex numbers, fine. I have this now, let us look at this set of all 3 cross 3 matrices. So, I have A and B belonging to set of, so remember M3 of R means, this means set of 3 cross 3 matrices with real entries, fine. So, given two matrices A and B which are 3 cross 3, I can add two matrices. I can talk of A plus B which will also belong to M3 of R. We have a 0 matrix, for every A we have a minus A, and we also have a scalar multiplication. Alpha times A also makes sense, and this is a 3 cross 3 matrix itself. So, therefore, I can think of this as a vector space over R. Similarly, if in place of the entries being real numbers, if it was complex numbers, I can talk in terms of complex numbers also, fine. One of the examples that I have not given you is 6. Just think of a vector with having just a single element V is to be 0, all right. So, 0 plus 0 is 0, alpha times 0 is 0, 0 is a vector here, all right. So, this is also a vector space over F, whatever F you want to take, real number, complex numbers, rational, whatever you want, you can do all of that, fine. 7. Let me define this set R of x. R of x is set of all polynomials in x with real coefficients. So, any element here looks like a0 plus a1x plus an x to the power n, and ai belongs to R, fine. 1 0 less than equal to I less than equal to n, fine. Note, there is no restriction on n, no restriction on the power, fine. So, this set will contain constants. So, this will contain, so 1 belongs to Rx, pi belongs to Rx, e plus pi belongs to Rx. We also have 1 plus 3x belongs to Rx, x square plus 10 belongs to Rx. We also have x to the power 100 plus 1 plus x square belongs to Rx. So, all of them they belong to Rx. So, any polynomial that you can think of, polynomial means finite sum, there is no infinite sum here, there is a finite sum, all right. So, look at any polynomial, polynomial means finite number of monomials, finite number of terms, fine. So, that is an element of Rx. So, given one polynomial, given another polynomial, I can add two polynomials to get another polynomial. So, therefore, Rx makes sense, the addition of vectors, addition of polynomials makes sense. I can also multiply by a scalar. So, every number gets multiplied. So, for example, 1 plus 3x times 2 is nothing but 2 plus 6x. So, you are just multiplying it component wise in some sense, and therefore, that also makes sense. So, set of all polynomials in x with real coefficients makes sense, and this forms a vector space over R. R because the coefficients are real numbers, all right. So, Rx forms a vector space over R. So, if I replace the coefficient by complex numbers, we will again have complex numbers, rationals and so on coming into play, all right. In the last two examples, if you remember, matrix multiplication is defined. Similarly, here polynomial multiplications are defined, fine. So, matrix multiplication is a meaningful object. A is a 3 cross 3, B is a 3 cross 3 matrix. So, I could multiply A into B to get a 3 cross 3 matrix, fine. But I am not bothered about those things, all right. We are bothered about only addition and a scalar multiplication. It has some extra things, let us not worry about those extra things, fine. We want to restrict ourselves to looking at only vector addition and a scalar multiplication. That is very important for us. Fine. Another example, fix n belonging to natural numbers. For example, take n equal to 3, all right. Then I talk of R of, I do not know what was my notation in my notes. Let me just look at it. Do I have a notation here, x and n? Yeah, this is the notation. So, this is a0 plus a1x plus a2x square plus a3x cube. ai belongs to R, 0 less than equal to I less than equal to 3. Fine. So, here we are fixing the degree of the polynomial is less than equal to 3, all right. So, if I have two polynomials of degree less than equal to 3, then I can add those two polynomials, and the degree of the polynomial is not going to increase because I am not multiplying. This is important. Since I am not multiplying, I am just adding two vectors. So, I am supposed to add only two polynomials of degree 3 or degree less than equal to 3, therefore, it makes sense. Fine. Similarly, a scalar multiplication makes sense. So, this is again a vector space. Vector space over R. Fine. Note, if we collect vectors, collect polynomials of only degree 3, then we have a problem. What type of problem do I have? All right. So, let us take a polynomial x3 plus 1, take another polynomial which is minus x cube plus x plus 1. These two are polynomials of degree 3. If we add it, fine, this x cube cancels out, I am left out with x plus 2, not a polynomial of degree 3, all right. So, there is a problem, is that okay? So, therefore, when you want to talk of polynomials, we have to talk in terms of polynomials of degree less than equal to some number. So, that is n that we are talking about here. So, we can fix it and then proceed, fine. Now, one very important example, you may be saying that what is new about it, we are looking at the same things again and again. That is true. Most of the times we will be looking at the same polynomials or same matrices, same vectors, same Rn and things like that. But there are places where things are different. So, let me take an example here. So, that example was 8. Let me look at example 9. I am going to look at this set R plus. R plus is set of all alpha belonging to R, so that alpha is positive, all right. This is my set. This is a non-empty set. Take any two elements here, alpha and beta. I want to define the sum as not alpha plus beta, but something else. So, I put a plus sign here to say plus is, this is not the usual real number sum. Real numbers are summed differently, this is not the same, all right. So, here I am saying that this is, I define this to be equal to alpha into beta. So, what I am saying is that 1 plus 2 is equal to 1 into 2, which is 2. 1 upon 5 plus 1 upon 5 is 1 upon 5 into 1 upon 5, which is 1 over 25. Is that okay? All right. The addition, the vector addition that I am defining, it has changed. Fine. So, here for example, in this example, 0 does not belong to R plus. So, I cannot talk of 0 plus something, fine, but I can talk of 1 plus any real number alpha, and this by definition is equal to 1 into alpha is alpha. So, this implies 1, or this is same as equal to alpha into 1, which is same as alpha plus 1. So, 1 is the additive identity. So, 1 is the one which works as something nice, fine. Also, alpha plus 1 upon alpha is alpha into 1 upon alpha, which is 1. So, the inverse, the additive inverse is 1 upon alpha of alpha, fine. And it makes sense because alpha is a positive number here, alpha is a positive real number, fine. I have defined a scalar multiplication. So, let me take A as a scalar, fine, and alpha as vector, fine. I can talk of this as defined to be equal to alpha to the power A. Alpha is a positive real number, A is a scalar, real or real number. So, whether it is negative or positive, alpha to the power A makes sense, all right. So, A can be our real number, A could be 0 also. So, any number to the power 0 is 1. If A is positive number, you will have positive powers. If A is negative, so A negative will imply I am looking at 1 upon alpha to the power A. Alpha to the power A will correspond to, so A is negative, so this is equal to say minus t. So, this will be alpha to the power t, fine, t positive. So, accordingly you can make sense and everything is done. So, you can show that R plus is a vector space over R. Again, you can make it a vector space over rationals and over anything, but important, this is a different vector space than all the vectors that I have looked at, fine. There are other vector space also, 10th, I will just give you the last one. I can think of this space Q of root 2 and root 3. So, this is the collection of all elements of the type A0 plus A1 root 2 plus A2 root 3 plus A3 root 6 and AI belonging to rational numbers. So, you can see that you can add two vectors, you can multiply by a rational number. So, this is a vector space over Q, fine. So, we will be looking at all the examples till 8, we will also look at some more examples future whenever we come across them. These two 9th and 10th are given to you to make you understand that just looking at plane R2, R3, Rn and items coming from there is not enough, fine. These are also very important ideas which give us different problems to solve at, to look at, and that they have got different applications. For example, this will tell us that how do I rationalize numbers. So, can I talk of, we used to talk of 1 plus root 2 multiplied by root 2 minus 1 by root 2 minus 1. What do I mean to say that I can look at 1 plus root 2 plus root 3 plus root 5 and so on. Here we do not have root 5, I can just include root 5, root 10 and so on, and you can look at things, fine. So, that is all for now. We will look at vector subspaces, linear span and things like that in the next class. Thank you.